Let me then get started. Well, thank you for the invitation to give this talk. I was told to give more of a, like a tutorial talk. So I have kind of made it at a, this is a very tutorial talk, but towards the end, I'll also show some of the results that we have been able to get in the last few years, some main results, just one slide each, not much detail. So this will not be very technical talk. And if somebody is an expert, maybe most of it should be familiar already. Okay, so this is Anand Jha from IIT Kanpur. I have an experimental lab in quantum optics and entanglement. And today I'm talking about this quantum superposition, entanglement, and the technologies that actually can come out of it. Okay, so here is the outline. I'll talk about the superposition, its basics, how it is different from classical superposition, and the applications and technologies that it leads to, or people think that it can lead to. And the second thing I'm talking about is the quantum entanglement. Again, it's basic. Is there any classical analog? And what are the applications we can have from quantum entanglement? So maybe let me just take the point. So in the history of quantum mechanics, the what led to quantum mechanics, first of all, is this question as to what is light. Again, I will not go through the entire history, but it is really this question as to what light is that led to the discovery of quantum mechanics and its development thereafter. So then, what is light? So after all these different years or centuries rather, the answer that we have is light is both wave and particle. This is actually very, very strange because when we think of wave, we think of something that is not localized, that is like everywhere. And when we think of a particle, we think of something that is somewhere, or at least in terms of center of mass, it is exactly at one location. So wave is something in principle which is everywhere. Particle is something which is exactly at one point. And light is both wave and particle at the same time. It is not sometimes wave, sometimes particle. It is light is both wave and particle at the same time. So this is now how we understand light is. So if I'm to kind of put what is the main difference between classical and quantum mechanics, the main difference is wave-particle duality. In classical mechanics, there is no duality. A system behaves either as a particle or as a wave. So for example, if I have a particle, I will describe it using Newton's equation and everything is happy. If I have wave, then I will describe it using Maxwell's equation and then everything is fine as well. But in quantum mechanics, we have a particle duality. That means a system can behave as particle and as wave at the same time. So it's like what Newton's equation does and what Maxwell's equation does. We will have to describe both in some way, and that job is done by Schrodinger equation. But the price that we pay, that the Schrodinger equation is now in terms of a psi, a wave function, a mathematical quantity of which we do not have much idea. But this mathematics gives the correct predictions for the results that we see in experiments. On the other hand, here the equation is in terms of electric field and the momentum, which is a real quantity that we understand what they are. But this wave function is just a mathematical quantity. Okay, so again, what is the main difference between classical and quantum mechanics? Classical mechanics handles wave separately, particle separately. Quantum mechanics handles wave particle together because wave particle duality is the characteristic feature of quantum mechanics. Of course, there can be other differences as well, but everything can actually be cast in terms of the wave particle duality. That is at the center. Okay, so just to give a feel for what we mean by wave particle duality, and I will try to have an example which can be seen experimentally. Maybe I'll try to show some real experiment or the recording of a real experiment so that to make it a little more convincing. So the question is, let's say I have a light bulb and it passes through a slit and then there is a screen after that. So what is the pattern I see? Well, since it's a slit, So majority of the light is blocked, and but some part of the light actually passes through slit. And we know the diffraction happens. So right after the slit, we'll have this kind of distributed kind of pattern. Fine. Now, if I reduce the intensity of this bulb, then what happens? Well, if I reduce the intensity of the bulb, the pattern remains the same, just overall intensity of the pattern decreases. If I reduce the intensity of the light bulb even further, then the pattern still remains the same, just that the overall intensity becomes smaller. What if I reduce the light intensity even further? So after certain point, after reducing the intensity by a certain amount, what we will actually have is no longer this continuous intensity pattern. We will actually see this dot structure. Of course, to be able to see this, one has to have a camera which is actually very, very sensitive, that can work at very, very low light level. But assuming one has that camera, if one does the experiment, then at high light level, one has this continuous distribution of intensity, which will keep on decreasing, but still retaining the functional form. But after a while, one will simply have this dot structure with complete darkness in the center. What if I reduce the intensity of this bulb even further? Well, then we have fewer number of dots. So this is what we see. So this is actually, already a feature of wave particle duality that you see. That of course we know the diffraction is a wave effect. Light spreads when it passes through tiny narrow openings. So we do see that. But when you come to this point, we do see the diffraction effect that yes, light does spread. But what we see is that the detection isn't happening at the single photon level, the dot structure. So we have this way, we have a particle and wave property both at the same time. Okay, let's do another example. Where instead of just one slit, we have double slit. This is much more familiar to most people. So this is the famous Young's double slit experiment. So I have light going through this double slit. So of course, on the screen, I have this bright and dark fringes. Fine. Now, if I reduce the intensity of this light bulb, then what happens? Well, the answer is probably clear that I will have the same pattern. The contrast remains the same, but just overall intensity decreases. Reduce the intensity even further. Contrast still remains the same, but the overall intensity decreases. What if I go even further? Now, at this point, it will be a dot structure. Of course, it has a structure that you can see. Of course, there's a more dots here, less dot here, more dot here, less dot. So you can see a fringe pattern, but this fringe pattern consists of which resembles this pattern that we see at the highlight level. But this fringe pattern consists of dots, and it's not a continuous intensity distribution. And if I reduce the intensity even further, I get fewer number of dots. So this is an example of wave particle duality that one can actually observe and see in the lab. And hopefully I'll try to show you some recording of some real experiment here. So what does this mean? We have done wave theory and superposition in classical mechanics. Now we are doing superposition in quantum mechanics and interference in quantum mechanics. So how are they exactly different? So the way superposition works in classical, the way we explain it is the division of amplitude. And the division of, for example, in the double slit experiment, you have this light coming here. Part of the energy, most of the energy gets blocked by the black screen, but part of the energy goes through this this slit, and part of the energy amplitude goes through this slit, and then we combine those amplitude to explain this interference pattern. Now, in classical mechanics, when you divide the amplitude, that essentially means division of energy. That you also divide the energy. But in quantum mechanics, what goes through, what starts from here is you can't say it's certain energy. You can just say it's a wave function that actually passes through. And if you can talk in the language of photon, then maybe you can say h bar omega energy starts from the bulb and goes through the slit. Now this h bar omega energy has a wave function associated with it. Wave function has an amplitude. Now that wave function amplitude, that does get divided at the slit. But however, unlike classical mechanics, the energy that does not get divided. Okay, so in the classical, division of amplitude implies division of energy. And the way how we explain interference is by superposition of those amplitude that gives me interference. But in quantum mechanics, the division of wave function does not imply division of energy. The entire energy has to go through one slit or the other, h bar omega energy if we are talking about. And the interference explained in terms of superposition of wave function. Okay. So if you summarize, then the classical wave theory is fundamentally incorrect. But this is applicable uh, at highlight level, inadequate at single photon level. So we can still use it at highlight levels, and we do use it at highlight levels. But this theory is inadequate at single photon level. So as a theory, it is fundamentally incorrect. But quantum theory, it is fundamentally correct at every level. But we typically use it only at single photon level. At highlight level, it will become much more complicated. So you still use a classical thing. But we have to keep this in mind that what is happening even at highlight level is this and not this. Okay, so how do you explain interference in quantum mechanics? So this is the explanation is very in terms of a very famous statement by Dirac that a photon interferes only with itself. Interference between two different photons can never occur. This is a very profound statement, but in some sense, this is very nonsensical, statement as well. Because in terms of meaning, what does it mean that a photon interferes with itself? It means nothing. We know that the photon goes through this slit or that slit, but it still interferes. So this is probably the best explanation, but even this best explanation is still very nonsensical as far as intuition is concerned. And the other way of saying the same thing, maybe we can rephrase it, is that the more we know about the particle nature, the less we know about the wave nature and vice versa. That's Bohr's complementarity principle. So wave particle duality, Bohr's complementarity, these are all pretty much the same thing, different ways of expressing the same thing. Okay, so this wave particle duality, of course, I've explained that in terms of photons because that's my personal favorite. But interference at single photon level single particle level has been seen not only with photon, but also with electrons. So this is a double slit experiment with single electrons. This is as of 2013, because these experiments are actually quite difficult. So theory were definitely known, but these experiments have been done only with better evidence only recently. So again, I will not go through the details of this experiment. There's a electron gun, you see double slit, and there is a detector. And if you look at the detector at different timestamp, in the beginning there are only few dots, just few electrons. Now more, but still no pattern. But after a while, although it is still a scatter plot, but you do see the maximum and minimum. And that shows the single photon interference. But this shows that, single electron interference. But this shows that the electrons did come one by one, that, you had just one either passing through this slit or that slit, but eventually it builds up the interference pattern that you do see at highlight level. This one is with not electron, but heavy molecule. How heavy? This is C10H4F17S. Is really heavy. And even with this, again, I will not go through the details of it. I mean, I don't understand that details, myself either that well. But what we see is that these are the individual particles, this molecule. But with that, we still see a nice interference pattern. This is as of 2019. So now only the technology is there to be able to do such experiments. So this is again an example of wave particle duality or interference at the single particle level, not single photon level, single particle level. Okay, so the other way of explaining wave particle duality is through quantum indistinguishability. This is indistinguishability argument is mostly used by Feynman. In that volume 3, he has used this term like a lot in order to explain quantum interference. And this and the Bohr's complementarity is kind of very connected. So I'm just taking a different setup, but it is explaining pretty much the same thing. So I have like a laser, and this is a Mach-Zehnder interferometer. So you have a beam coming in or a photon coming in, splits that into two. Part of it goes this way, part of it goes this way, combines, and then they have a camera. Fine. Now, if I'm doing things at the single photon level, then this laser, well, at this, how the, okay, let me just explain how interference happens. So in a Mach-Zehnder interferometer, you have light coming this way or that way, and then you kind of combine. But you do introduce a tiny angle between the two. And if that is the case, then at the camera, you will see the interference pattern, spatial interference pattern like that. So, but if you don't introduce that tiny angle, then also you will see interference, but that is a little difficult to observe because then you have to move this and the interference will come as this whole blob being there or not being there. The entire intensity will actually fluctuate here and go from maximum to minimum and so on. But here we just introduce a little angle between the two beam and then we can just see interference right over there in terms of this fringe pattern. Fine. So with that, let's start the experiment. So I have this source being like a single photon. It comes if to a beam splitter, then it needs to decide. Now in classical mechanics, you have half of whatever comes at a beam splitter. You have half of it going this way, half of it going that way. So it's like dividing the amplitude, and division of amplitude also means division of energy. Now, in quantum mechanics, as I said, you have wave function. Wave function you can divide in terms of amplitude, but division of amplitude does not imply division of energy. Meaning, if I'm thinking of it in terms of photon, which means h bar omega energy, then after coming to the beam splitter, this entire h bar omega energy has to decide whether to go this way or that way. So the entire energy goes this way or that way, even though we will write the wave function here as a superposition wave function coming from there and from there, but the energy that never gets divided. The entire energy goes either this way or that way. Okay, so now in terms of this indistinguishability argument, if these two paths or if these two photon paths are indistinguishable, that means just by being here, just by being at the detector, if there is no way I can tell whether the photon came this way or that way, then there will be interference pattern. Okay, so if this is a detector, that's a starting point, and if the photon reaches here in two different ways, that's only when the interference happen. But if these two photon paths are indistinguishable, that's when we will see interference. Now, so let's just do and if the photon paths are not indistinguishable, then we will not see interference. Okay, so what does that mean? So let's do it. So we have photon, and this photon is vertically polarized, for example. It comes to the beam splitter, it remains vertically polarized. It can go either this way or that way. Even if it goes this way, it remains vertically polarized. It goes this way, vertically polarized. Now, if you detect a photon here, is there any way we can tell whether the photon came this way or that way? We cannot, because if we detect the photon here, we'll find it to be vertically polarized. If it is vertically polarized, then it could have come this way or that way. That means the photon paths in this situation are indistinguishable. And if the photon paths are indistinguishable, we will see interference. Fantastic. Now let's put a half wave plate here. Now what a half wave plate does is changes the vertical polarization to horizontal polarization. Okay. Now if the photon comes this way, it goes as vertical, 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 vertical. But if the photon goes the other way, it's like vertical, 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 but horizontal. Okay. So now if I detect a photon here, I detect it. If the photon came this way, it will have a horizontal polarization. If the photon came this way, it will have vertical polarization. So by measuring the polarization of the photon coming this way, in principle, I can tell whether the photon came this way or that way. So the two photon paths are not distinguishable. And if the two photon paths are not distinguishable, then I will not see interference pattern. That is indistinguishability. Now, in the same setup where this is H and V, it combines at a beam splitter. Let's put a polarizer here. So it is still H and from this side and V from this side. So it's coming here. I put a polarizer at 45 degree. Now, if I detect a photon here, that means I will detect the photon as 45 degree polarized. So in this case, will there be any interference? That is a question. Now, if we just notice, if I detect a photon, it has to be 45 degree polarized because it's coming from a polarizer at 45. So if I find a photon to be 45, which way it came, I have no way of telling, because if it is 45, it could have come from vertical like this and give me a 45-degree polarized photon, or horizontal like this and give me 45-degree polarized photon. So just by putting a polarizer, I have erased that information, whether it was, I have erased the information as to which way the photon came in. Now I will only detect it as 45-degree polarized photon, and I will have no way of telling whether it came this way or that way. So the two paths are not indistinguishable, because if I didn't have it, then it was not indistinguishable, but I have it. This is not distinguishable. That means it is actually indistinguishable. And then you will have the interference actually back. So this is the idea of quantum indistinguishability, or you can also say quantum eraser, that by putting this, you have erased the possibility of being able to distinguish, and then that makes it indistinguishable, and hence you can actually get interference pattern. Okay, so in summary, what we have is a single photon interferes with itself. In classical, we explain interference by division of amplitude, which by default implies division of energy. This is fundamentally incorrect, but at high light level, we do use it, but it is completely inadequate and incorrect at single photon level. On the other hand, quantum mechanics is correct at every level. It works in terms of division of wave function, which does not imply division of energy. And we explain interference in terms of the superposition of wave function. But we use it mostly at single photon level and not at high light level. Okay, so if we want to summarize, we can just say single photon interference can be explained only in terms of each photon interfering with itself. Okay, so are there any questions before now? I need to change the topic. So if there is any question, I can take. If not, I can continue. Okay, so before actually I go next, maybe I want. Yeah, go ahead.
Anand, I am Prasad here.
Yeah, Prasad, yes.
Hi, I have a question. You see this
Mhm.
in case of this double slit or more than double slit experiments, there is a identity which involves which path, coherence, and entanglement. We have, I think myself and Sabis, Tracy and others, we have derived this one. There is a Nature Photonics paper in this year, February 2025, that verified it. And there is the exact relationship between which path, because you have put the path detector. Are you
Prashant,
aware about it?
Prashant, your voice is not very clear. Maybe can you come slightly closer to the mic? I'm having a hard time.
Yeah, let me do that. Yeah.
Uh,
Huh? Okay, so am I audible now?
no, fantastic. Yes.
See, Anand, there is a
Mhm.
nice relationship, in case of double slit and more than double slit, between which path and coherence and entanglement. Interestingly, entanglement comes from there.
Mhm. Mhm.
Then so this Kabis Qureshi, myself, and some of our teams have done it. It's a 2022 paper, which is verified experimentally in a Nature Photonics paper this year.
Okay.
So I bring that paper to your attention because I would like to see in your experiment how entanglement signatures shows up.
Okay. Please send that. I'm
I
really
will do.
interested.
Yeah, I
Yes.
will. Yeah.
Okay.
Okay.
And right now, I just show you, this actually I do as a demonstration in the, classroom when I teach quantum mechanics. This we do, this is a real experiment we do in a classroom. So depending on what the paper has, maybe we can even do the experiment. So I'll just quickly show you this real experiment. This is basically the double slit setup that we have. But this is just this setup. But we are simulating this double slit using a spatial light modulator, and there's a attenuated helium neon laser so that we have the one photon one by one. And I just wanted to kind of show this experiment. So here we have this experiment. Again, the detail is not there, but the moment I run it, it is a real experiment live demo. There's a student sitting here that will kind of get up and start moving. This is a screen where we actually frame by frame record, and this is a screen where it is actually accumulated. Sorry, or maybe it is the opposite. So let's just run it. Just keep an eye. It will start. you're getting dot structure. So this single dot, this just appears and blip because this is a frame, this is accumulated one. You see this is an individual photon hitting the detector in every frame. So in every frame, just one photon you can actually see very clearly. Sometimes there's none. Maybe
Yes.
once in a while it is two, but I think per pixel it is less than one per frame. And then the accumulation, is happening over here. So it is very clear that the photons are coming one by one. No doubt there. Of course, I just see the scattered pattern. No details further. This is a 15 minutes video. I will not run it. I will just
Okay.
go quickly through. Otherwise, take a lot of time. So now you see still this dot structure, but maybe some semblance of bright and dark we can
Yes, sir.
start seeing. And now if I continue, this is still one photon per frame, less than one photon per frame. Now I have slightly better. I just continue, but I can maybe even increase the acquisition. Maybe I have I'm collecting more photons per frame. This is still less than one photon per pixel, but more photon per frame. And now I can see this interference pattern and even continuous intensity pattern because of the accumulation. So this is really a single photon experiment at the single interference at the single photon level that we can actually demonstrate inside a classroom. Takes almost 10 days preparation, but it is actually worth it when we actually do it. Yeah.
This happens.
Uh,
I'll send you the paper. Let's discuss
fine,
online.
fine, 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 fine. Okay, so let me just continue then. Right. Right. Well, I showed you single photon interference. Well, this is some fun stuff we have done. This is actually showing if the video works. Probably have happened yet. Oops. It's fun that we can. The bird. Fine. Okay. So now let's go to the next topic, which is quantum entanglement. That was quantum interference. This is quantum entanglement. Now in quantum, let me just try again by coming. Okay, this one, let me just try again. So this is actually about 10,000 photons that we have. This is on a camera. We are putting on a spatial light modulator. We just make a pattern on it. We call it a dancing photon. And if you change the structure on the SLM, then you have this 10,000 photon, dancing. So when I do the demo, you can see this 10,000 dot structure is not a continuous intensity pattern, kind of moving this way. So just for the single photon interference and how we can actually handle it. Okay, I'll stop here and then go further. Okay, so next is quantum entanglement. Now, what is quantum entanglement? So a popular level description, which is of course incorrect now, is like if you disturb one particle, both of them get disturbed. So that is the very popular notion of entanglement. This is of course captures only a little bit of it and not completely. And of course, Einstein objected to this kind of phenomenon. So what entanglement actually is, this is just one way of explaining it, is that let's say we have a light coming out of this narrow opening, so wave diffracting from a point. For this one, we can see is that we know the position very well. The photon came from here, but the momentum, because the diffraction is completely uncertain. So in this situation, we can say the delta x or position uncertainty is 0, but the momentum uncertainty is literally infinity. But when you have a plane wave, it has a fixed momentum value. But a plane wave, the transverse position of the photon can be anywhere. So this situation, you have delta p equal to 0, delta x equal to infinity. And in general, of course, you have delta x. So I mean, the point here is I was trying to make is if you reduce delta x, delta p increases. And the limit is set by the Heisenberg uncertainty relation, that is delta x, delta p has to be greater than h bar by 2. This is the Heisenberg uncertainty relation. And that is a very basic, very basic principle of quantum mechanics. And the basic principle you should not be able to break. This is actually true in general for any two non-commuting operators. So in 1935, 90 years ago, Einstein, Podolsky, and Rosen, uh, Einstein, Podolsky, Rosen, oops, where is it? Sorry about that one. So Einstein, Podolsky, and Rosen, they constructed this theory where we showed, well, let's just see what that theory is. So they considered this system of two particle, which had a common path, but now they are space-like separated in the present. And they said, okay, let's have these two particle have a wave function psi, which has in this form. It is the IPX x2 minus x naught by h bar, it is the IPX1 by h bar. So that is a wave function they considered. Of course, this is a momentum eigenfunction with value p by h bar, or p we can say. And this is another momentum eigenfunction with momentum minus p. So this essentially says when the particle has one has momentum p, other has minus p, and so on. The same wave function can be written like this in terms of this is a delta function, this is the eigenfunction of position, and here you have similar kind of constraint. Of course, this cannot be written as a product of the wave function corresponding to the first particle times the wave function corresponding to the second particle. But for this wave function, one can actually show that the uncertainty in the position of the first particle, given that the second particle has already been measured, times the uncertainty in the momentum of the first particle, given that the second particle has already been measured, is less than h bar by 2. So this does violate Heisenberg uncertainty principle. And Einstein, Podolsky, and Rosen, they pointed out that here is an example from quantum mechanics that seems to be violating the very first principle of quantum mechanics. And that this use this example to actually question whether quantum mechanics is complete, or maybe then they suggested that maybe it is incomplete and maybe it requires additional hidden variable to explain measurement results. Well, now we know that this suggestion of hidden variable theory is not possible through that 2022 Nobel Prize violation of Bell inequality. So this is not possible. So quantum mechanics as it is complete. And this fact is now taken as a signature of entanglement in position and momentum. So delta x times delta p conditional being less than h bar by 2, that is now considered as a signature of position momentum entanglement. Just like position momentum, one can also have a entanglement in time and energy, and also angular and orbital angular momentum. For those who are not familiar with orbital angular momentum and angle, so angle is just like angular position variable we define. And for orbital angular momentum, if you have a mode like this with the e to the IL phi kind of phase profile, azimuthal profile, then for such mode, if you take enough mode volume that the energy is h bar omega, that the corresponding orbital angular momentum turns out to be h bar L. Again, I will not go into the details of it, but angle and orbital angular momentum form a Fourier pair, and they can also give me entanglement, angular orbital angular momentum variable. And these are all referred to as continuous variable entanglement. You can also have discrete entanglement, that is polarization entanglement. For example, I can have a state psi, which is written as HH plus VV. The same state HH plus VV, of course, 1 over root 2 for normalization, can be written in the 45 minus 45 basis like this. HH plus VV can be written as 45, 45, 45 plus minus 45 minus 45. That means both the particles are either 45 or both the particles either minus 40. I've seen both these bases, both this state, it cannot be written as a product of psi wave function corresponding to first particle times the wave function corresponding to the second particle. And this inseparability is always a signature of entanglement. And for polarization, in this case, it is called polarization entanglement, which is a discrete form of entanglement. All these examples were the continuous variable entanglement. And I'll try to give some intuition as to how we see what polarization entanglement is. So this is a very simple example, and through that I will also try to explain what is hidden variable model. Again, I will use no math, almost no math. So let's do two experiment. And what is the experiment we're doing? I have a source of, well, I will have some measurement results. I will have some measurement result that somebody has measured in the lab, and we'll try to explain it either through quantum mechanics and through hidden variable model. So this is the quantum mechanics, this is the hidden variable model. Okay, so here is a measurement outcome number one. So what is the measurement? So the experimenter finds that if the signal photon, this is a photon number one, photon number two, here also photon number one, photon number two. In the quantum mechanical, the quantum entanglement model, these are sources of entangled photon. In the hidden variable model, these are two independent, these are photons coming from independent sources. They can have some rules, but things are not entangled. Okay, so the first measurement outcome is that if the signal photon or the first photon is measured to be horizontally polarized, second photon is horizontally polarized. If the signal first photon is measured to be vertically polarized, second photon is also vertically polarized. Now, this measurement outcome, how can be explained using quantum mechanics? Well, very easy. If I have a wave function that looks like this, h plus vv, that explains this measurement outcome. That whenever signal is h, idler is h, signal is v, idler is v, and so on. Now, can two independent sources also produce such correlation? Can it be explained? Let's see. So if I have these two independent sources, but let's say I have the rule that both sources emit simultaneously and emit the same polarization. Okay. The second rule is 50% of the time both sources emit horizontal polarization. Third rule, 50% of the time both sources emit vertical polarization. And with this experiment measurement outcome can also be explained. Is this entanglement? No. Why? Because I can have a hidden variable model. That means these are two independent sources can also explain. So that is a separability, and hence it is not entanglement. Okay. Let's do another experiment. The outcome here is if signal photon is measured to be 45, idler is 45. If signal is minus 45, idler is minus 45. Can quantum mechanics explain it? Yes. If I have a wave function like this, quantum mechanics can explain it. Can a hidden variable explain it or two independent sources? Yes. What are the rules I need to have? Very similar. Both sources emit simultaneously and same polarization. 50% of the time, both sources should emit 45, and another 50% of the time, minus 45. With this, I will be able to explain this measurement outcome. Is this entanglement? Of course not. Third measurement outcome. If the signal photon is horizontal, idler is horizontal, signal is vertical, idler is vertical. And if the signal is 45, idler is 45, signal is minus 45, idler is minus 45. So both, all four at the same time in same experiment. Now, can quantum mechanics explain it? Yes. What is the wave function? hs plus vv. Well, this will explain only these two, but this will explain these two, but these two are anyway equal. So this wave function can explain all four. Excellent. Now, can I have two independent sources be able to produce such outcome? What, and if yes, then what will be those rules? So this rule is basically the aim of any hidden variable model. And in this case, actually, it is not possible to make such a rule, a set of rule that actually can explain this measurement outcome. So, I mean, if somebody in my course, I actually tried that I give this as out as an homework problem that somebody can do it. You get an A star without giving a, the end sem exam. But of course, this is not possible. So is this entanglement? Yes. So simultaneous correlation in two different bases, for example, here HB and 45 minus 45, that is what is needed for entanglement. Okay. So what I did is a very, very intuitive, semi-intuitive way of kind of explaining without any math. But of course, a lot of people had put in a lot of math. With David Bohm is the front runner there for making hidden variable theory by following the suggestion of Einstein, Podolsky, and Rosen. And in 1964, then Bell put up an inequality, and if it could be violated, that would mean that the hidden variable interpretation is not possible. So of course, that was done 1969 by Clauser, then by Aspe 81, and then by many others later. And then finally, the 2022 Nobel Prize to Aspe, Clauser, and Zeilinger went for the violation of Bell inequality. Okay, so the one of the most widely used source of entangled photon is this parametric down conversion. So you there's a nonlinear crystal, you absorb one photon at higher frequency and then emit two photons, signal idler at lower frequency with conserving the energy and so on. This is called the parametric down conversion, which has energy being conserved, momentum being conserved, and so on. Let me just skip this basics of nonlinear optics part. But if you want to study more of parametric down conversion and phase matching and how it works with a fully quantum mechanical treatment, we put up this tutorial article, and this should be able to. This is at very low level, but this gives you complete, very rigorous calculation, almost 20-page tutorial article. These are the results that we have seen in our own lab, and that we have put up in this paper. But we have also put up for type 1, type 2. This is a web app on my website. You can actually, no download needed. You can just play it there, the different phase matching conditions and so on. But let me just skip it. Okay, so these are the continuous period on discrete entanglement. So what is it useful for entanglement, or is there any use, at least currently or futuristic? So several potential use of entanglement, and maybe potential technology. First is quantum computation, communication, quantum lithography, cryptography, teleportation, imaging, a lot of application. And maybe I'll try to go through some of the examples, some of the main algorithms that we have in the field of all these. So let's start with quantum lithography. I'm skipping computation because that is a whole different field. So quantum lithography. So there is this effect called Hong-O-Mandel effect. It's a very simple effect. You have a blue photon, a parametric down conversion gives me two entangled photon. If I mix them at a beam splitter and then collect them in coincidence. So there are four possible ways in which these two photons arriving at a beam splitter can reach the two detectors. Both the photons gets transmitted, both the photons get reflected, one reflected, one transmitted, and vice versa. These are four possibilities. But it turns out if I have these two entangled photons and if they arrive simultaneously, that means no, this length is equal to this length, then these two possibilities are gone. You are left with only these two possibilities. This is because of quantum interference. And so what we find is that in this case, both the photons either go this way or go that way. And this is called the bunching of photon. As a result, if you move this beam splitter, and then when beam splitter is x equal to 0, that means these two path lengths are equal, then there's no coincidence because both the photons are either here or here. Coincidence means one here, one there. But of course, if you introduce a delay, then the interference, destructive interference is not perfect, and then you start seeing the coincidence. And this profile is also called the Hong-O-Mandel dip profile. Okay, so this fact can be used for doing what's called quantum lithography. But before we do quantum lithography, let's see what is classical lithography. In classical lithography, you have a light. I'm doing it at the single photon level. You have beam slitted. Part of it goes there, part of it goes that way. And then you combine it at an angle on a substrate. And then the pattern that gets written here is of this form 1 over cosine 4 pi x by lambda, where lambda is the wavelength of light. So you can write a pattern like this. And of course, how many such maximum minimum pattern you can write on a chip decides how many transistors, for example, you can actually write in that chip. So less is the period, more is the resolution, and more is the number of patterns that you can write. So, but given a wavelength, there is a constraint as to what is the finest pattern you can actually write. If the lambda is there, then that already puts a constraint. But if of course, I can write finer pattern by reducing lambda, but there is a limit as to how much lambdas can be reduced. But so if the lambda is fixed, one can still write finer pattern if I use entanglement. How? So let's say these are the two entangled photons arriving at a beam splitter. Now, these two photons, if they arrive simultaneously because of Hong-O-Mandel effect, both of them will either go this way or that way. And now in this case, if I work out the math in terms of two photon absorption, it turns out to be 1 plus cosine 8 pi x by lambda. So lambda is same. It is 4 pi x. Here it is 8 pi x. This is a two-fold enhancement in resolution. And if you continue, if I have n such photons, which right now nobody knows how to do, but if you have n entangled photon and if you do lithography, I get an n-fold enhancement in resolution. So this is known as quantum lithography. With n equal to 2, I think it has been demonstrated, but beyond that, it has not been possible, even though it was proposed in 2000. Okay, well, quantum cryptography. This may be familiar to many of in the audience, so maybe even I can skip that quantum cryptography. This is very popular. The quantum cryptography, I'll just show you the quantum cryptography. It was shown in 2000 now, and then in 2000 between two islands 4 kilometer apart. And in 2017, this was from a Chinese group. This is from the ground to satellite. At that level, it was actually shown. Okay, so next is quantum teleportation. Again, I will not use any math here, but the idea is very simple. That let's say A and B share an entangled photon, and there's a third party C. The particle C has a state psi, which neither A nor B has any idea about. But the point is, can A send this state onto the state of particle B? And that is the very idea of quantum teleportation. So in quantum teleportation, you don't teleport the quantum state, you don't teleport the quantum system, but you just teleport the quantum state. And if I want to give a very commonplace analogy, it's like this person, that person is a certain smile. And if we are to, in teleportation would mean that we are not teleporting the person, but we are kind of teleporting the smile. So this will be after teleportation. So in quantum teleportation, the system is not transported, but the quantum state does get transported. Well, this requires a Bell-state measurement. I will not go through the details of it. In 2012, over 143 kilometer against Zeilinger group, it was actually shown, proposed in 1993. Okay, so the quantum imaging, I'll just go through this one. There's a lot of ideas in quantum imaging that have come more recently. This is a very strange idea, which is based on this 1991 paper by Mandel from Rochester. See, he introduced the idea of induced coherence. Well, based on this idea, now in 2014, this idea of quantum imaging with undetected photon. Now, I will not go through it. There's not much time. But what we have here is that they are using two entangled photon, this yellow and red. Now, this red photon goes through the object and comes like the second crystal and gets dumped. It is not measured. So the photon that goes through the object is actually dumped. But the photon that does not see the object goes there, and then these two detectors we look at in coincidence, and we can actually see the object. So this stencil was what was put in here, and this red image was constructed out of this detection. So that's why it's referred to as quantum imaging with undetected photon. Now, this is the paper work from 2023, very recent, experimental quantum imaging distillation with undetected light. So it is the same idea of the induced coherence. And here you have an object embedded in a lot of noise, and using quantum entanglement, you're able to actually distill it out of that. And here the noise, the background noise is 10 times more than the signal, but you're still able to do it. This is again 2023. This is information encoding in the spatial correlation of entangled twin beam. So you encode some information into the pump, then it gets down converted, and after down conversion, you are able to actually recover by doing a correlated measurement. This is an this is 2024 science one. So adaptive optical imaging with entangled photon. So adaptive optics, those of us who are familiar, is widely used in astronomy, where you use a guide star, and then for an unknown object, you correct the wavefront aberration. Here, that is done without using guide star. If you use entangled light for illuminating the object, we can actually correct for aberration. This is the setup, and this is the object without aberration correction. With aberration correction, it looks like this. Again, I'm skipping the details, but just the entangled correlation is being used for adaptive optical imaging. Okay, now I'll just go through in the last 5 minutes, maybe, some of the results that we have in our own lab. So we have been working on state detection in high dimensional basis, and especially the orbital angular momentum basis. So in 2017, we showed this result the first time, that we now have an orbital angular momentum detector, with which, by just taking two intensity images, we can measure orbital angular momentum mode of up to 80 dimension or 100 dimensional state with very, very good accuracy. Following up on in this work, we could actually do it only for the diagonal mixed state. That means incoming state had to be of a certain form, and then we were actually able to measure it. This we have published just this year, 1 month or 2 months ago. Now we can take any density matrix, and of that density matrix, we can find the spectrum. And here, like a modified interferometer that we have, is a little complicated than our 2017 work, but this works. That works only for the diagonal mixed state, but this works for any state. And here also we can go the dimensionality up to more than 100, and with very high fidelity, 99.85. An extension of this work, which here what it is basically an orbital angular momentum detector, a broadband uniform efficiency orbital angular momentum detector for single photon. Now we're trying to build a broadband uniform efficiency detector for 2 photon. So why is this even useful? Well, it has both the aspect. One is, of course, this will let us handle high dimensional entanglement, two photon entangled state. And the other, it can let us answer some fundamental question. And one of the fundamental question is OM conserved in SPDC? There are theory works showing that OM is probably not conserved in SPDC, but so far there's no experimental verification of that. And the reason for that is probably so far the detector that was being used was based on SLM and singular fiber, and which is not that accurate, but this is a very, very accurate detector, although very difficult to implement. With that, very recently we have seen that actually OM is not conserved in SPDC. Experimentally, we see the non-conservation up to 42%, but theoretically it can be even as high as 56%. But this is an ongoing work from our lab. We have also shown a technique for measuring 2 photon entanglement with single photon detection. So not doing coincidence, but just looking at single photon detection, I can measure delta X, delta P, and get the violation of conditional violation Heisenberg uncertainty. This is the number that was the best in 2022. And this is the work again from 2022, where we showed that there is a certain form of entanglement, that is orbital angular momentum entanglement, that actually revives upon propagation. So the entanglement, when it's generated, there is entanglement, but after a while you lose entanglement, but it comes back again. And so if for entanglement, even if you introduce turbulence, it is able to, bypass that just by propagation. That is the result we saw there. Some imaging results we also have. This is showing basically certain type of light sources that we have made, and that gives us a propagation invariance kind of resolution. This is a more recent work, not published yet, in which we have done imaging in noisy background, which the noise is 20 times more than the signal. And so what we have shown is that if you do imaging through correlation, that means typically you have an object and a lens, and then you measure the intensity. That is the intensity imaging. But you have if the image is encoded in the correlation function and you retrieve it through correlation function, and then that is referred to as correlation imaging. So if there's no noise, intensity imaging is as good as correlation imaging. But if there is noise with intensity imaging, you can't see anything. But correlation imaging, you can actually see the thing. It's like, can you see the moon during the day? And the intensity wise, of course not, but correlation wise, maybe yes. So this is how the photos in a lab look like. We also do quantum awareness initiative at IIT Kanpur, where we actually set up experiments, transport that to the the labs. It is actually very, very time consuming. It takes an effort. And then after transporting, you set that up in a lecture room. Of course, I need a lot of student volunteers. And then make sure that experiment is working and do the demo using all the projectors and so on. And then show them this. But once it is done, the kind of questions, the number of questions you get is just simply infinity. It is just really fantastic. And then at the end of it, everybody wants to come and have a look at it, and you have to save your equipment from that crowd. It is very difficult, but it is actually worth doing. Okay, and very quickly, I could just also say that I'm part of the National Quantum Mission, where we are doing this entanglement enhanced quantum imaging, where the aim is to develop entangled photon sources, detectors, also develop quantum imaging protocol, and have benchmarking to tools to make sure that it is actually quantum advantage and not just classical advantage. So here is a National Quantum Mission team. I'm the lead PI. Then we have 4 from IIT Kanpur, 2 from IIT Ropar, 1 from IIT Delhi, 1 from SN Bose. And what I have shown several works is this is my group, and they have been part of many of that. So in summary, I have shown you what is superposition, entanglement, and some of the technology that can actually come out of it. And thanks to these funding agency, IIT Kanpur, DST Quest, CRB, and also more recently DST NQM. And thank you for your attention. Thank you.
So, thank you, Professor, for such a nice and informative talk. I think our students, particularly students, have got enough background to start the quantum optics, how to start some basic experiments, and then. So now with this, now the floor is open for some questions. If there is some questions, then the professor can answer.
Let
So,
me just, Anand, let me ask a couple of questions.
Okay.
This teleportation experiment,
Mhm.
if that can be used for showing quantum monogamy. This
Mhm.
if the state is maximally entangled, then the unknown state, for example, once you do the Bell measurement, what will happen is that the unknown state and Alice will decouple, the maximum entangled state, and the Bob will get the unknown state information, right?
Mhm.
But if it's not maximally entangled, see, this actually happens because of monogamy. Because
Mhm.
if Alice and Bob are maximally entangled, no unknown state cannot go get in. The moment it tries to get in, then Bob will decouple. So
Mhm.
if you look at it carefully, it is actually because of entanglement monogamy.
I
Therefore,
see.
the same experiment in a mixed state kind of scenario, if it's a mixed state, obviously the state will not completely decouple. This monogamy identity probably can be analyzed using that same apparatus also.
I see. That I don't think anybody has tried, right? Not a maximal entangle Bell state, but a mixed state. That I don't think anybody has tried. Yes.
I have not seen any.
Yes, and in fact, in this National Quantum Mission, and at least last few years that we have been doing, I mean, I didn't do that since my work properly. But what we have seen is that there is a unique set of advantage that you get if you use partially coherent field in imaging, at least. And in the quantum language, the partially coherent field is essentially the mixed state. So very similar advantage should also come through the mixed state. So I think that is a very interesting observation. I don't think anybody has shown, but it probably will be worth doing that.
I must say that I really enjoyed your talk, and I do
Mhm.
see a lot of things which I would like to understand from you.
Mhm.
But I think
Mhm.
that I share that our paper and also the 2025 lecture properties paper.
Yes,
And
yes, yes.
then we discuss because some more things I'll ask you later.
Fine, 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 fine.
Can I ask a question? This is Asima here.
Yeah, Asima, yes, yes, yes. So good
Yeah,
to
hi
see you
Anand. Yeah.
there.
Yeah, no, I have a simpler question. I don't
Ah,
understand too much of it, right? But I was just wondering, this experiment that you do on with interference, how easy to is it to do it? I mean, obviously you're doing it in the labs also, I believe. Hmm. So how easy is it to do it, and how much? What would be the cost? Because I mean, here there are people who are working on this quantum in the quantum center. So I was just wondering whether they could do these experiments to show it to students. Demonstration as a demonstration, maybe.
okay.
Uh,
So well, very, very nice question. Again, I have also been trying to do it here in a sustainable manner, but it is, unless I get a proper fund, it is not possible. But to quickly answer your question, it
mm,
actually takes a while. So maybe, see, doing it in the lab is much easier. But if I have to do it in a classroom where the actual with the demo mode, it takes about 10 to 15 days preparation, because you have to think of everything. You have to also save your equipment and so on. So far I have done demo at least 6 times, 5, 6 times. Each time I have taken the stuff from my own lab. So I think approximately 50 lakh worth of equipment.
I see.
Major is basically a single photon detector. That is the major cost of equipment. But of course, since you want to show the effect very clearly, you have to have very good quality kind of even the smaller equipment. So 50, 60 lakhs, I would say, is the budget. But if I'm doing it out of my lab equipment, it is actually very, very difficult to manage. But if I can get, let's say, 50 lakh fund, then it can be set up on a cart, a smaller optical bench, and then that setup just remains. And then if I can do demo every 6 months or 15 days, then it doesn't take much. But building that and preparing that, in my case, I've been doing that, building it, preparing it, and it takes 15 days. And after that, I just destroy it because I do need that equipment for my own research. So that is definitely not sustainable. But if one can have about 50, 60 lakhs, then maybe even 2 experiments can be done in the same setup.
I see. I see. Excellent. I mean, it was very nice listening to you. And yeah. Okay, that's
Thank you.
good. Thanks. Let's
Thank
see. I mean, if
Thank you.
they
Thank you.
decide what they want to do, but yeah. Thanks.
Thank you.
Sir, I have a question. Actually, I am trying to understand. So, when you are showing that interference between two H and V, and just to see so that there will be no interference when the photons are H and B polarized, orthogonally polarized. But in terms of polarization, if you try to look some polarization interference instead of looking at the intensity interference, so will that from that looking at that polarization interference, can you get some results what I'm saying is yeah, in this particular experiment in this slide. So I'm saying by looking at the polarization fringe pattern, can you say something about the source like these two interfering photons? Between any information about those interfering photon pairs?
If I understood your question correctly, see, this indistinguishability argument, this is Feynman's favorite, and then he uses that. So the whole idea is that even in principle, just by being at the detector, but one has to define what the detector is. And in this case, the detector is like after this polarizer. So
Okay.
being at the detector, if I can tell, even in principle, not it doesn't have to be experimentally, even in principle, if I can tell whether the photon came this way or that way, that means there is a distinguishability. That means I can distinguish. And if there is distinguishability, there is no interference. If there is indistinguishability, that means if I cannot tell, then there will be interference. But even if I forget about this distinguishability and indistinguishability of Feynman, if I just take the wave function and so on and keep track of everything, including its time, orbital angular momentum, polarization, one can actually work out polarization interference, time interference, space interference, angle interference, everything can be worked out, no issue.
Okay, sir. Okay. Thank you so much, sir. Thank you.
Thank you. Thank you.
Is there any more question from the student? Uh, if no more question, then let us thank Professor Anand Kumar Jha once again for his nice talk. So,
Okay. All right. Thank you.
thank you so much,
So
sir.
thank you.
Yeah, thank
Thank
you
you.
for your valuable
Okay.
time.
Okay.